We have built our bridge of light. Using ordinary least squares, we found the best linear unbiased estimators. But our journey is only half complete, because our estimators are derived from data containing random errors. The estimators themselves change from sample to sample. They are inherently random variables. This is the ultimate problem of inference. Without knowing the exact probability distributions of our estimators, we cannot test our hypotheses, and we cannot relate our sample guess to the true population. We are trapped in a symphony of chaos, surrounded by the discord of a million unseen variables affecting human behavior. How do we find the shape of this noise? To find harmony, we invoke a cosmic mathematical order, the Central Limit Theorem. This theorem proves that when a large number of independent random forces collide, the distribution of their sum tends to form a perfect symmetrical shape. We assume that our unobservable disturbances, the chaotic errors of reality, follow this grand design. We assume they are normally and independently distributed, and by adding this single powerful assumption to our crucible, we create the classical normal linear regression model. The clutter of random noise begins to hum into a beautiful symmetrical chord, the bell curve. But what exactly is this shape? To understand it, we must first understand a concept called standard deviation. Standard deviation is a mathematical measure that tells us how closely or how widely individual values are spread around their true center. The mean. Imagine measuring the exact heights of millions of people in a massive city. Most people will cluster around the average height. But as you search for people who are extremely tall or exceedingly short, you will find they become rarer and rarer. And from this natural pattern emerges the perfect symmetrical slope of the normal distribution. The bell curve dictates that within just one standard deviation from the center, 68% of all the chaos is contained. Expand your net to 2 standard deviations, and you capture roughly 95% of all possibilities. At 3 standard deviations, 99.7% of the universe's randomness is perfectly accounted for. It is the ultimate architecture of predictability. With the bell curve hovering over our data, our ordinary least squares estimators are elevated to a higher plane, because any linear function of a normally distributed variable is itself normally distributed. Our estimators now follow exact, predictable, normal probability distributions. They are no longer just blue. With the added assumption of normality, they become B.U.E, best unbiased estimators, the finest estimators in the entire class of estimators. We finally know the exact shape of our guesses, and with that knowledge, we gain the power to conduct precise statistical trials using t-tests and f-tests, regardless of the sample size. But a rival composer enters the hall. This is the method of maximum likelihood. Instead of minimizing squared errors, this highly theoretical method asks a completely different question. What specific parameter values maximize the probability of observing the exact sample data we have collected? Maximum likelihood works backward from the final symphony. It studies the resulting sheet music and attempts to deduce the truest mathematical notes that could have created it. A different philosophy, a different path toward truth. Here is the ultimate revelation of the classical normal linear regression model. When the rival composer, maximum likelihood, listens to the data under the assumption of the normal distribution, the mathematical sheet music it writes becomes perfectly identical to ordinary least squares. 2 entirely different methods, 2 completely different philosophies, yet under the harmony of the bell curve, both yield the exact same golden parameters. From discord, we have found absolute, undeniable harmony.